Let's go over the answers for Chapter 16, Practice FRQ number 2. Now this is dealing with a molecule called arsenic pentafluoride, ASF5, and I just put a picture of it here just so we can kind of get a feeling for what the molecule looks like. Not important to the problem. Now we start off here with a very straightforward kind of a problem, but old stoichiometry problem, so answer the following questions. A 55.8 gram sample of arsenic pentafluoride is introduced into an evacuated 10.5 liter container at 105 degrees Celsius. What's the initial molar concentration? So just have to go back and say, well, here's ASF5, and so for ASF5 we need to figure out its molar mass. So arsenic, you look it up on the periodic table. Fluorine is 19.00 times 5, add it all together. Now we just go ahead and say, if we know the grams, you can find out how many moles of arsenic pentafluoride there is. Now the actual problem, however, is not what's the number of moles, it's what's the molar concentration. So we have to go back now and say, take the moles divided by the liters, and we get our first answer, which is the molar concentration of ASF5. So far so good. Next part is what's the initial pressure in atmospheres of the ASF5 in the container. And you start saying, well, they're asking for pressure, and we know the volume. We calculated the moles up in part 1. The temperature, we've changed that to Kelvin, and we always know R is 0.0821 liter atmospheres per mole Kelvin. So hopefully by looking at those, he's recognized, well, this is a PV equals nRT problem, and solve for P, substitute in the numbers, and you get an answer here in atmospheres. So even though this is an equilibrium chapter, they use the gas laws, and that's a pretty common thing to watch out for. Now, we get back to our next part, and that is at 105 degrees, okay, arsenic ASF5 decomposes into ASF3 and F2. And when that happens, go ahead and write the equilibrium constant expression in terms of molar concentrations. So they're saying write the Kc as opposed to the Kp. We could go both ways on this because they're gases, but just write the expression. So that's an easy point right there. Now part C, it says when equilibrium is established, 27.7% of the original number of moles has decomposed. So calculate the molar concentration of ASF5 at equilibrium. So that we want these equilibrium values down here. So we can say, well, this is really just stoichiometry. We knew what the initial concentration was, 0.0313 molar. We got that from way back in part A. And so we say, well, if I have 27.7% of 0.0313, just multiply 0.277 times this, we get this number here, 0.00867. So we're going to go back now and say, well, let's subtract. So we're saying that this much decomposes, so minus 0.00867. I'm just going to call that 87 because of my digits. And if I do that calculation, I'm going to get 0.0226 molar. Now, for this row here, if I use up 0.0087 molar of my ASF5, I must be making 0.0087 and making 0.0087. And if I start with 0, then I must end up with 0.0087 molar and 0.0087 molar. So just being clear and neat, we get values for each of these. And what we're looking for is calculate the molar concentration of ASF5 at equilibrium, and that's the answer that we're trying to get. So we put a box around that. For II, when we say use the molar concentrations, calculate the value of the equilibrium constant. So now we can just go back and use the values we just made. So this is going to be 0.00 0.0087 for ASF3, 0.0087 here, divided by 0.0226 for my denominator. And that will come out to be 0.003349, and let's write that as 3.35 times 10 to the minus 3. And either of these answers would be perfect for this part. So we can calculate our value of KEQ. The final part of this problem says calculate the mole fraction of F2. Okay, the mole fraction of F2. So we want moles of F2 over the total number of moles. So way back from part A, we've calculated that there were 0.328 moles of ASF5 put into the container. So again, we know that 27.7% of that amount decomposes. So I get a number like 0.091. So it's minus 0.091, and if I'm using up that much, I must be making 0.091 and making 0.091, and these are all moles. Now remember, the icebox can be done with moles, it can be done with molarity, and if we're talking about gases, it can also be done with liters, since liters and moles are proportional. So these last values here are 0.091 moles, 0.091 moles, and I'm going to stop and calculate this first one. This turns out to be 0.237 moles. So mole fraction, which is symbolized by capital X underline of my fluorine, is the moles of my fluorine, 0.091, over the total, which is 0.237 plus 0.091 plus 0.091, and this comes out to be 0.091 divided by 4.19, the total moles, which would be 0.217 mole fraction. Phew. So this is not really a hard problem. It's really mostly stoichiometry rather than equilibrium. And we just have to keep track of our ice boxes, write numbers clearly, and don't get too messed up. Good luck.